All right, welcome to Robotics 311. This is lecture 6. Today we have like a few things to discuss. We're going to go just quickly review over the Solidworks operations. Talk about creating assemblies, which a number of you asked me about. Talk about thermal modeling, and then we do a quiz. One quick question for you guys: did somebody lose 100 pounds? I assume of British currency in this room. Okay, if you did, or hear somebody who did, this would be on Tuesday. So like they sent me a note saying someone in here or the next class lost 100 pounds. Okay, so good. I don't think it's you guys. Couple like announcements, just quick thoughts. Be sure that you look at the MATLAB code that we talked about that does this kind of analysis framework for the ballbot. So it does ballbot mechanics, it uses the motor that we selected, and it shows you the current and voltage. We went through that a couple lectures ago. Just make sure like you look at it and kind of understand how that process is what we're learning, and then we did it for the ballbot and selected the motor that was used. I didn't spend a ton of time on talking through like why we selected this pull loop motor, why it has a 70-to-1. Like there are other options. With the motor size, really there's not much. It's the biggest motor that sells, the 37D. So that was pretty much our only option, but we could have chosen a few different transmission ratios, and 70 seemed about right. We were originally also looking at 100. I don't know if you remember, we were looking at these current and voltages. There's certain transmission ratios that are available. We chose 70 and it fit well based on this framework. But if you go to Pololu's website, it has all the characteristics of the motors. I'd rather not spend kind of more time on that. So that's why we skipped it, but it's all there. So take a look at that code. I think it will help you kind of crystallize this framework and how it fits into the ballbot. The planar modeling, our current plan, so we've done like some mechanical modeling of the ballbot. That's going to come into play a lot when we talk about control. So when we start doing control, kind of after we do kind of building and making, we'll get into controlling. And that will use the ballbot planar model that we use, and we'll go deeper into it. We could have done that first, but I thought that would be like a little too much too fast. So we did kind of a one-plane example, or one-plane version. We should use that to showcase how we model the system and select motors and transmissions. And then when we do control, we're really going to need a full model of the system. So that's going to come back up later. I would be kind of interested in your guys' take on how, once you kind of more through the class or more through the class, how we like laid out the different things that you're learning, like in the order that we did. And all of this is new. So if you guys think to yourselves, oh, it would have been better to learn that here instead of where we talked about it, that's information that I would really like to know. A couple of hints on question 5. We extended the homework deadline till Tuesday. When it says the spring and damper are rotational, that means you don't need to worry about their lever arm. They're just modeled as k theta instead of k, L over 2 sine theta. Yeah.
So in this case, does that mean we don't have a dampening for the motor? It's just like a dampening on the output?
No. No, you would still use damping in the motor, and you'd use the spreadsheet to include that. This just also has a damper on the output of the transmission. But
I don't think we were given the values for like the damper of the motor.
It should be in the spreadsheet. For that one, do I provide all the parameters?
Oh, yeah, because you did provide like everything of the motor and like resistance and
So I write everything but damping?
Yeah.
Okay.
Damping's on there.
Let's add damping in there. So I'll like send a parameter out. Just include it. It'll be something small, but include it just for completeness. I'll like provide a version of that homework with the damping value in it. For now, just consider it to be like something really small. Yeah, thanks for the heads up. Okay, so you can model the spring and damper as a rotational element, so you don't need to worry about its linear distance traveled. You only need to worry about its angular distance traveled. And then remember we talked about sort of reflecting inertia from the outside of a transmission to the input to the transmission where the motor sees it. And we said, okay, the inertia on the output of the transmission, it sees that divided by n squared. And that came because both torque and angle were both affected by the transmission ratio. So you end up getting it divided by n squared. But that's also true for other mechanical elements, not just inertia. That applies to stiffness and it applies to damping as well for the same exact reason. That their functions, they depend on both torque and displacement. So they will be divided by n squared. Yeah.
How come for like
So for this example, you're saying we need to divide by the n squared, but on the catapult example, when we went through the current, we didn't need to divide by n squared on that damping.
There was no damping in the catapult.
Wasn't there the
On
we
the
still had
motor, there was a damping, but there wasn't damping on the output was just the torque to do the lifting task.
Okay, so we're saying there's damping actually on the physical oscillator here?
Yeah.
Okay,
So
gotcha.
there's a little picture of a rotational spring and a rotational damper that's indicating that those are on the output. So the catapult example had damping on the motor, but not damping on the output.
Okay.
So that's why you didn't see it
So
there.
this one is just damping on the oscillator, not on the motor.
No, it'll also have damping on the motor. I just didn't provide you that value, which I'm going to share. Cool? Does that make sense? Yeah.
So just to double check, so you only do the divided by n squared when the force is acting not on the motor, it's acting on the leverage arm or whatever the motor is acting upon.
That's right. And it's not that it's a force, it's that it's a mechanical element, like inertia.
Okay.
Or stiffness. So like a force would just reflect through by divided by n. But a mechanical element, something that's affected by both its motion produces a torque, and those end up getting divided by n squared because of the motion is a factor. Yeah.
So just to be clear, when we're taking into account efficiency of the transmission,
Mm-hmm.
we would only use that for when we're doing it for forces.
Right, the torques, yep. The torques on the output of the transmission will have to be lower than the torques on the input of the transmission, so we divide by that efficiency.
Okay, thank you.
Yes. Great, okay, so yeah, so that problem was maybe like a little, it was a challenging, homework problem, really the only one that was kind of difficult. The challenge is a lot of it turns out in the modeling, so I felt good about extending it. That gives you a couple more office hours. I have office hours today, and then Eve also. Cool. Okay. So a couple hints on homework. Question 5. Okay, so these were we're just going to kind of quickly review the different operations. So some of you are experts at Solidworks, and so a lot of this is a review for you. So this class is probably not aimed at the expert. You'll just know that. So this is for people who are new to Solidworks, and the people who are very strong with Solidworks will just have to hang in there. But we talked about these different operations. You can create 3D operations. There's also 2D operations of sketching. The 3D operations require a sketch, and you can do things like extrude, revolve. You can loft, which will take something from one sketch to another sketch and kind of connect it. These are just different operations to create 3D structures. If you stack them, you can create more complicated structures. There's other types of modeling in SolidWorks that's not based on these types of operations. We're not going to learn that, but just so you know that they're around. There's a whole class of modeling that's based on surfaces instead of on volumes. But that's kind of that's pretty advanced SolidWorks. We're not going to do anything like that. So you guys would just know you can create features. You can create negative features or cutting features. That's how we build 3D shapes. Those shapes require a sketch. You guys got the hang of that yesterday. You create sketches, add lines and curves, add smart dimensions and relationships to kind of make those sketches what you want. Generally, you want to take a blue sketch to a black sketch. What did black mean?
Defined.
Fully defined. Yes. Awesome. We talked a little bit about this is convert and offset. Those are just really helpful sketching tools in addition to kind of smart dimension. Yeah.
So just when you say things are fully defined, we had this yesterday where I would create a relation between two different lines and I would think that would fully define it, but that still wouldn't fully define it. So what is there's just fully defining, what does that mean?
That would be probably in a plane, it would be 3 degrees of freedom have to be constrained.
Okay.
So it can rotate and translate. So all of the relationships have to go back to those degrees of freedom and constrain them.
Got it. Okay.
So if there's sometimes it's just challenging to know whether these operations have how many degrees of freedom worth of constraints.
Right. So just if you constrain something rotationally, that doesn't mean they're constraining it along translational.
Right. And if it's blue, you can always grab it and drag it, and it's going to move. It's going to do something. It's going to change size or move around. But when it turns black, you won't be able to change it. these were kind of like the general layout of the ballbot, the different structures, what you guys are making. I kind of just wanted to show this also again to see if there are any questions about the different components or how the ballbot's laid out. We gave you some part files to start with. That I think will help you. And then also, we're going to give you today all the other files. So for those of you who want to start making assemblies and kind of making sure your holes are in the right spot, so we'll give you these standoffs, these motors, Omni wheels, a Raspberry Pi, the battery. So we'll kind of like provide these files to you, and then you can add them when you want to. Any questions about the ballbot structure, what's inside of it, what you're making? Okay, so a lot of you asked about creating assemblies. This is how we do that. So assemblies are like a different class of file. There's part files, there's drawings, which we haven't talked about, and there's assemblies. So when you open Solidworks, you click on this assembly, it's going to prompt you to create a new assembly. That'll be blank, nothing in it, and you have to add things to it. When you add a part to an assembly, we have to define how the parts fit together. That's the key part of an assembly. We call those mates. So relationships called mates are added to assemblies to define how it comes together. You add parts. If you create an assembly, then you have to like add parts to it. There's nothing in it. You add parts by clicking Insert Component. It'll bring up this dialog. You select your component, and then it'll insert it into the assembly. Once it's inserted, you're just placing it. So it'll give you like your mouse will be able to place it anywhere. You click your mouse and it drops it in the assembly, but it has no constraints or relationships. So it still has 6 degrees of freedom. So once added, place it in your workspace using your mouse. And the parts added to the assembly have 6 degrees of freedom natively. So they have 6 degrees of freedom. Without 6 degrees of freedom with the constraints, they're able to move around. The first thing you put in there, I think, is locked. And everything will have relationships to that first part. And then you can still define, like there's a difference in coordinate axes from that first part to the assembly, which has its own axes. You can kind of align those if you want. But I think once you insert your first part, everything will sort of align to that first part. So your constraints, so the constraints added, or I'll say mates. Mates have to constrain all 6 DOFs, unless you want your assembly to be able to move. So you'll end up adding mates, the constrained in 6 degrees of freedom. The way SolidWorks adds mates, so this is adding mates, is not that they're done by degrees of freedom, they're done by like intuitive relationships, which is actually like super helpful. So mates are added by selecting the mate button, and it brings up this little dialog. Here's like 2 parts, for example. If I select on this face, and then I select on that face, I'll see those faces populate here, they'll light up, and then it'll give me some options about how to constrain those. If I select 2 flat faces, for example, it's not going to let you select a concentric mate. So it provides options for mates based on their physical function, not their degrees of freedom, and those physical functions just constrain multiple degrees of freedom often. And it kind of goes increasing numbers of degrees of freedom constrained as you go down this list. And eventually you can lock it, which just fully constrains it in all degrees of freedom. Okay, so I'm adding these files to the lab folder for lab 2. So these will be like the parts that you have available that we're giving you. We're going to give you the solid models 2. They'll be back in that lab folder for lab 2. And then this shows all the different mate types available. So you just kind of keep adding them until it does what you want. So like this, what kind of mates do you think you would use if you were trying to mount this to this? There are 3 required mates. Or one option would be made it 3 times. And I fully define it. How many holes does this thing have on it? 3? Yeah.
I was gonna say that I would do a concentric mate with all 3 holes, so all 3 mounting holes.
That's one, okay, so that's one way to do it in one operation. select those 3 holes, make them concentric, then actually that would not constrain it. You still need one, yeah, you'd still be able to go up and down. So you still would need a coincident made between those 2 faces, but that would work. In fact, then you would only need 2 of those holes.
You could also just make it parallel to the whole surface and then match up one of the holes if you're using
Yeah. You could even select, so you can select faces. So for these holes, we could select the bore of the hole. We can also select edges or vertices. We could select like the top. If we select the top of the circle for the mounting hole and the top of the circle, the bottom of the circle on the mounting or on the mount, then that would, I think that might be able to do it in one mate, but it's still, it might make them coincident and concentric. But yeah, that's how you do it. You kind of like add these mates till there's enough mates that it fully defines it. And if you click on it, you can move it around. It's not fully defined. Okay, any questions about adding mates? Okay, this is the end of our review. Now, let's talk about where we are and kind of progress to thermal modeling. Okay, so where are we in this? We're kind of working through this design framework. We've done sort of understanding our application requirements, how we specify that depends on the application, but we as the engineer kind of make those choices. We talked about mapping the application requirements to the requirements on the motor. So this is the motor's torque and speed. We're going to convert that to the motor's current and voltage needed. Now we're going to learn how to talk about that in terms of the motor's temperature. So we have learned the basics of understanding requirements and what our robot needs to do. We use those requirements to make design decisions. Now we want to confirm that our design is viable by investigating a thermal response. Where does this thermal input come from? Why are we talking about thermal response? Where does this thermal input come from? Thermal input. Why is it getting hot? Yes, it's coming from the resistance of the motor. We're getting joule, it's called joule heating. I squared R loss is called joule, it's joule heating is another name for it. We have joule heating from the motor's windings. There are rules of thumb to kind of shortcut this analysis. Which we'll look at the end, which we'll do like a steady state analysis. Why are we learning this prediction of winding temperature? Because it's relevant to system designs where mass is an important factor. And these are important concepts for robot designers to know. That's why we're learning this. I think this is important stuff. Like this is like a little bit of physics, a little bit of engineering, but it's good stuff. It's important stuff for people who work in the design of robots to be very familiar with. Okay, thermal modeling. We're gonna kind of go through this. We got 4 or 5 slides on different thermal types. It's a crash course in heat transfer modeling. Heat flows, so it's generated by the windings. It's going to heat up the windings. So heat flows from windings to the housing to the atmosphere. So we kind of our modeling of heat transfer has to understand how heat's flowing. Windings, housing, it's going to heat up the metal of the motor, and when that motor heats up, it's going to send that heat to the atmosphere. There's 2 types of heat transfer that we're going to learn: conduction, convection. What's conduction? Anybody know? It's sort of on the screen. Yep.
Conduction is like when it spreads across the surface or like the metal.
Yes, so this is conduction. It's heat flowing within a material. So we heat up this bar, heat's going to flow to the other end. It's happening through a process called conduction. So we'll say heat energy flowing in an object. And then convection, what's this? Yes.
Like heat energy flowing through like a fluid.
Yeah, that would count. That would be, so like this is convection here. Fluid is air. So what happens is it heats the air up, that air rises, it pulls cool air in. That process just continually repeats itself. That's convection. That's a different process. That's not heat flowing through a material. That's heat coming off into the atmosphere. This is transfer of heat energy between an object and the environment. What's awesome about this is that both of these forms of heat transfer have the same governing equations. If we understand these equations, we can then predict winding temp rise. And that's what we're going to do. Let's start. Conduction. So let's learn the governing equations for conduction. Okay. Conduction, we're going to say heat flux, Q of T in watts. Also called like thermal power. That's I squared R, it's a power loss. From the winding resistance, that's the current or heat flow. Q comes from I squared R loss. So we have a bar. Let's consider a bar of kind of length L, temperature sigma 1 on one end, temperature sigma 2 on the other, heat flowing from one side to the other. In this class, we use sigma as temperature because T is like torque. So we're going to use sigma. So anything that has a sigma is a temperature concept. There we go. Okay, that was weird. Okay, so to talk about how heat flows, to understand these governing equations, we need to know a little bit about the thermal physics. So the property that describes conduction is the thermal resistivity. So thermal resistivity, this is in K per watt, degrees Kelvin per watt. Is below using thermal conductivity kappa, which is in watts per meter Kelvin. So the thermal resistivity, our sigma, would in this case for this bar would be L over A kappa. So this is saying, okay, this is the thermal resistance of this bar. Heat is going to flow in this bar, but it's going to flow based on resistance, like thermal resistance provided by the physical properties of the bar. Yeah.
What are the units of K? I just can't read the. It's watts per
Meter Kelvin.
meter.
Yeah.
What is the K thing on the numerator? The bottom link of the line.
This.
Oh, I mean, for R sigma.
What is this?
Yeah.
It's this.
Oh.
It is the thermal conduct. This is a material property, thermal conductivity. This is an example of creating a thermal resistance from the different physical properties of a piece of metal.
So the form is just kind of like electrical resistance.
Yes, that's where we're going. So what I want you to know here is not that you need to memorize like what the formula for the thermal resistivity of a bar. What I want you to see here is that there's a concept called thermal resistivity. It governs how heat flows through an object. That property is governed by the physical material and its size, shape. A. That's its cross-sectional area. Yeah.
Is there a reason why thermal resistivity is proportional to the length? I don't see how that would.
Yeah. So just imagine. Now imagine this bar is really long. We want to not only know the temperature here and here, we want to know the temperature anywhere along this length. So what this is saying is that the temperature would linearly progress from Q on to Q2.
And
Sigma 1, Sigma 2.
you also may have mentioned this is A, the cross-sectional area.
It is.
Okay.
Oh, yeah, so it's a property of the physical geometry of this piece of metal, this conductor. This is kind of the more important part. This says that the thermal flux flowing through it is equal to the difference in temperatures divided by the thermal resistance. Does that look familiar? What does that look like? What? Ohm's law. This is Ohm's law for thermal circuits. So this is actually a circuit. So we can think of thermal systems as electrical systems. The law that governs heat flux and its relationship to temperature and thermal resistance is the same as the law that governs current, voltage, and resistance. Yeah.
What was sigma again?
Sigma just means temperature. It's what I'm using to separate these electrical properties, thermal electrical properties, from their actual electrical properties. So if you see a sigma, it's a thermal property. So what this says is if we want to know temperature, so if we know Q and we know R, we can begin to get an understanding of the temperature change across something. that has, we know its thermal resistance, which is a function of its shape and material properties. We know Q, based on Ohm's law, we can begin to get an understanding of temperature rise. This describes the mechanics of conduction. This is how conduction works. It's just like an electrical circuit. It's just like a resistor. Let's talk now about convection. Convection is similar but different. So now instead of having a bar, for example, we have a mass, an object, and an atmosphere. The object has temperature sigma 1, the atmosphere has temperature sigma 2. What's going to happen here? So heat's radiating or coming off of this, flowing off of this object into the atmosphere. So we should have some information about there should be heat flowing if sigma 1 is greater, and it's probably going to have something to do with its area, since heat is flowing out of its area. Convection, again, convection has identical governing equations. So where do you think this is going? It's going to Ohm's law. We're going to get there a slightly different way. So consider an object in the atmosphere, surface area A, convective heat transfer coefficient H. So instead of the thermal conductivity kappa, we have a different sort of material property that's governing the flow or the thermal resistance in the case of convection. And it's the heat transfer coefficient H. So in this case, our sigma is 1 over HA. Do I want you to memorize this formula or this relationship here with this cube? No. But what I want you to understand is there's heat that flows through a different mechanism, not conduction, flows through convection. It has a thermal resistance, just like conduction. I want you to kind of understand that that thermal resistance is governed by these properties and can be used to predict temperature. Yeah.
Is the convection heat transfer coefficient dependent on like the fluid it's surrounded in or dependent on the material that is radiating?
Great question. Which do you think? Or like,
I think the fluid that's surrounding it.
so if I take this thing and instead of having it sit in air, I have it sit in water, it's going to transfer a lot more heat. Agreed? The density of the water will pull a lot more heat. So it depends on the fluid, but it also depends on the material. So if it were styrofoam, it's going to have a much harder time conducting that heat into the water. But if it were metal, it's going to be a lot easier. So it's dependent on the situation that the heat is going from the object to the atmosphere.
So to know the coefficient, we have to know like both the material and the fluid that we're putting in, and so people have to like how to calculate it for every combination, or is there a way to like?
The way that we would find this out, we'll get to this part, but we wouldn't try to calculate it in this way or model it. We would determine it empirically. We don't ever, no one really ever tries to model it from material properties. Okay, so Q is still going to be sigma 1 minus sigma 2 over our sigma. Same thing. Okay. Our sigma for convection can be changed. Agreed? We just talked about how we could change it by soaking the system in water instead of air. What's another way to change it? It's really common. Yeah.
Increasing the surface area.
And what do we call like something that does that? We have a name for it's a noun. A thing that does that. It does exactly that.
I got another word for it, like a heat sink.
Yeah, it's common. A heat sink can be changed with heat sinks. So sometimes this comes up. In fact, it's possible that we end up putting heat sinks on your motor drivers so those chips get hot and we might have to dissipate that heat. But yeah, one of the great things about convection is you can change the resistance by adding heat sinks. So a lot of people do that. Heat sink the motor or they heat sink the drive. That's really, really common and helpful. And it actually works really well. Like a small heat sink can change the thermal conductivity a ton, or the thermal resistance a ton. Okay, one more element. So it's not just heat transfer, we don't have not just these two forms of heat flowing. We have to talk about one other thing, which is heat storage. So thermal capacitance is the term that we use to describe this, sometimes called thermal mass. And it describes an object's ability to store heat energy. Its thermal capacitance, C sigma, is mCp. So heavier objects store more energy, store more heat energy when they're heated up. That makes sense. And then Cp is the specific heat of the material. So that's the material property. So we have this object here, we're heating it up, we're gonna put some heat into it. And we want to describe what is this governing equation? It's capacitance. Any thought about what this has to be? Anybody know? If I solve for Q, it's going to be C sigma d by dt with sigma 1 of t. Let me draw that as an electrical circuit. Okay, so this is the electrical circuit that describes the dynamics of a thermal capacitor. This is a current source. So here in this electrical circuit, we have a current source charging a capacitor. If we wanted to look at the temperature of this object, we would look at the voltage here. So we have two resisting concepts that actually have the same governing equations. So we know the concepts of thermal resistance, and we know two mechanisms to model heat transfer. And now we may also have to model the thermal mass that heats up. And we have an expression for that. And if you guys are comfortable with resistors and capacitors, it's going to be pretty straightforward. Voltage. So we talk about the relationships between the thermal world and the electrical world. They're directly analogous. In fact, we could actually also talk about it in terms of anything else. Pressure. Voltage is analogous to what in a thermal circuit? Voltage and something are the same. Yeah. Temperature. Hopefully that makes sense. Temperature is a potential. Just like voltage is a potential. It has the ability to do work. It's an effort. Current is analogous to,
Heat flux.
heat flux. That's a flow variable. What's another flow variable? Yeah. Velocity. Yes, current, thermal flux, velocity, angular velocity. These are the things we used to say they're flow variables, and effort variables are the potentials that do the work. Force, torque, temperature, voltage. Okay, yeah.
Weren't before though torque and current related and voltage and velocity related, or do I have this flipped in my head? Like when we were talking about kind of like when we were modeling the motor. So are they now here with heat though its voltage is related to the effort? Because before weren't we just saying that like flow is the velocity?
Yeah.
And then but that's current, so then wouldn't then current be related to velocity and not voltage related to velocity like we were saying before? Or is it because these are like different, like this is thermal and that's opposed to like converting an electric world to like a physical movement?
So current is the resulting flow that comes from an effort. Same thing as with heat flux, same thing with velocity.
Okay.
What, so like, I think I'm missing your question.
I was just kind of confused because like before we were relating voltage to velocity, like when we were doing the graphing, we were kind of saying that voltage is analogous to velocity.
Yeah, okay, I see your question.
Yeah.
So what's happening there is that the governing equations for a motor swap.
Okay.
What's mapped to what.
Okay.
So they sort of exchange the effort of flow. That's something that happens in a motor, but the products of this both are still power. Like all of this is all still true. Efforts are efforts, flows are flows. But in the governing equations for a motor, it does use the effort variable in the flow equation and vice versa.
Gotcha. Okay.
Yeah.
Thank you.
So I'm expecting this class to be comfortable modeling resistors, capacitors. Okay. How do we model a thermal response? Now I want to do an example with you where I show these equations, we put them to work, and we put them to work in an example that models a motor. So how do we use this to model motor thermal response? We're going to develop a thermal circuit. I'm actually going to, it's going to take a second. Okay. So this is my model of a motor. This is our motor thermal model. We have a winding in black. It has a resistance and an inductance. We're not using inductance for this. But inside that inductor is a copper core that's kind of heating up. So the joule heating is coming off the windings. It's heating up the steel or iron inside the motor. And that's kind of around the windings. And that heat flow is kind of flowing out from there, heating up the housing, and that's flowing out into the environment. This is the housing, this is the windings, so heat's going to flow from here to here into this thing, and then from here to here in the ambient. So that is a motor. So if I want to draw this as a thermal circuit, I'm going to draw a simplified version. It might look like this. Where this is sigma winding, this is sigma housing, that's sigma ambient. This is C sigma winding, this is C sigma housing, this is R sigma winding housing, this is R sigma housing ambient. So all we did now, we learned these kind of original tools, conduction, convection, they are resistances. We learned that mass heating up stores energy, it's like a capacitor. So now let's create a thermal circuit that models this full system. We have the winding temperature at this voltage. We have a mass, that's the mass of the copper of the windings. It's thermal resistance that describes its heat flow from the windings to the housing. We have the temperature, which is the voltage here. The temperature, this is the housing temperature. And we have the mass of the housing, its thermal resistance as heat flows from the housing into the atmosphere. We have the temperature of the atmosphere. I usually do this. I set this temperature equal to 0. What does that do? If I set that equal to 0, what effect does that have on these temperatures or those voltages? Makes them relative to ambient temperature. So now it's describing a temperature increase above something like probably 25 degrees C, not ambient temperature. So if I set this equal to 25, everything will be in actual temperature units. If I set this equal to 0, it's a little bit easier to manipulate the equations, and now it's a temperature rise. What generates heat flux? Pretty sure you guys are with me here. I squared R. Is that R an electrical resistance or a thermal resistance? Electrical. Okay, how do we predict heat flux? So this is a little bit, like this set of equations will be a little more challenging to analyze, but I'm gonna show you how I'm gonna analyze them. This is a simplification. Normally this capacitor, like if this were a true model, this capacitor would go to ground, not go here. But it's a little bit old, you'll see it's a little more convenient to analyze that way, and it's very close. Okay, so how do we predict temperature? You can use this governing equation. Okay, you won't have to solve this. This is the time domain version of this equation. I basically solve both of these for Q and set them equal. So this could be rearranged to solve for the temperatures, and then you could find the solution by finding a solution to the differential equation. I'm not going to do that, but that's how you would solve this. There's actually a much more convenient way to solve it using transfer functions, but we don't learn transfer functions in this class. So I'm going to show you an example of transfer functions. You're not going to be required to know it, but I'm going to give you the file. So you'll be able to use it, even if you don't necessarily understand the backbones of how transfer functions work. This class is done in the time domain with differential equations, so that's why I provided that. You won't have to do an equation with a capacitor, like on an exam. That's something without transfer function analysis, it's pretty challenging. So I'm not going to have you do that. But I do want you to see this, and we'll talk about what you will be required to do after that. Yeah?
What's the character on the very far left of the equation?
This guy?
Yeah.
That's C, sigma W. That's this. Here, I'll do it in pink. This guy is this guy. Yeah.
What are the two different R's?
The two different R's are like one, this is conduction, this is convection.
Okay.
So this R is describing the literal flow of heat from the windings to the housing by physically touching and being part of the same material. So that's a conduction, but they have the same, they have the same gravity equations, they're still resistors, but this is a resistor describing convection, this is a resistor describing convection, a flow of heat out of the atmosphere, yeah.
I thought the conductors were what kind of shows the convection. Or the capacitors, excuse me, not the conductors, sorry. I thought the capacitors were the things that were kind of showing the convection, because isn't that what we said was equivalent, or?
No, the capacitors are showing the actual heat up of the metal.
Okay.
And when the metal heats up, it stores energy.
Okay, so we're having the housing heating up as well, or excuse me, the winding and the housing storing up. Or
That's right. This is the mass of the housing, this is the mass of the windings. It's driving those. Which do you think will be slower and which one do you think will be faster? Who thinks the housing will be slower? Who thinks the windings will be slower? I don't know, half of you answered. It's the housing will be slower because it's heavier. You remember what governs those properties? The mass was a big factor. So the dynamics that govern this side will be slow, and you'll see that in a second. The dynamics that govern this side will be very fast because the windings are light. They don't have a lot of mass to heat up. So they heat up quickly and they don't store a ton of heat, so they cool down quickly. This is convenient for transfer function analysis. Who knows what a transfer function is? Okay, so this is not, I'm going to show you this, but it's not going to be something you're going to be required to use. Yep.
So earlier when you were talking about the thermal capacitance, you had the equation as QT is equal to C times ddt sigma, h sigma.
Yep.
So then for this one, when it's ddt of like sigma minus sigma, what is
What's
that?
going on there?
Yeah, what's that?
Okay, what that's saying is, like this, I'm going to talk about in terms of the electrical world. So like this has a voltage drop, this has a voltage drop. This voltage drop is defined against 0. So the voltage drop across this is only related to this temperature.
Okay.
This voltage drop is not coming from 0, it's coming from here. So if we want to calculate the voltage drop from here to here, it's sigma W minus sigma H.
Okay, so then is that like physically, is that like the difference between the windings ability to store heat versus the housing?
This would be actually like literally the temperature of the windings minus the temperature of the housing. So it would be their temperatures. The voltage drop is the same thing as saying the temperature drop or the temperature drop. Yeah. Other questions? Yeah.
So I guess I'm just slightly confused about the notation for the heat capacitor. Like in electrical circuit, our capacitors have two different plates which have different potentials, but the heat capacitor seems to just be a single block of stuff. So like why can we still like write it as something that has two leads?
Say this again.
So like why can we write the heat capacitor as similar to an electrical capacitor when it is just a single block of stuff instead of having two separate plates that are like isolated?
It has to do with the governing equations that describe what they do. So that'd be like saying, this is the same thing as saying if I compress a spring, it stores energy. So we have to know like how does that energy get stored? So this governing equation or the equations that govern the capacitor only like describe that. And it happens to work that they are the exact equations for a capacitor. But that is this concept of how like they're all linked. Energy storage in a capacitor, energy storage in a spring, energy storage in like an accumulator. All of that is energy storage in the temperature of a heated object. Those concepts, that's all system dynamics. There's a whole class that kind of describes how all of those relate together. Yes?
Sorry, one more question.
Yeah.
So on the left-hand side, why is it 1 over R instead of sigma W minus sigma H over R?
What are you saying?
Like on the left-hand side.
It really should be, I forgot to write this.
Oh, okay.
Oops. It really should be that. Thank you. Okay. Let's say you want to model these things. Where do we get this information? Where does it come from? It comes from motor data sheets. This is an example motor data sheet from a company called Maxon. Maxon makes outstanding motors, both brushed and brushless. This happens to be a data sheet for a brushless motor, but all of the concepts are the same. So like it tells us, like all of the information is listed here. If I blow that up and I show you on that side, let me see if I can zoom in. you see this? This tells us all the information that we just talked about. Thermal resistance, housing to ambient. Thermal resistance, winding to housing. Thermal time constant, winding. Thermal time constant, motor. Max winding temperature, 155 degrees C. Okay. Now I want to show you an example, but before I do that, I want to kind of talk you through something. These analyses can be completed in Simulink using transfer functions really easily. So what I've done is upload this file for you. So you can use it if you're interested. It is the exact Simulink model of the problem we just drew on the board. This is a transfer function that governs the winding housing temperature. This is a transfer function that governs the housing ambient temperature. This sums them together because it's just basically two systems in series. And then this tells us the winding temp. I'm gonna pull this up for a second, but what you can do is kind of pattern match. So these are of the form R sigma over R sigma, C sigma plus 1. There should be an S there. An S there, so I'll add that later. So then this is also the same thing as R sigma over tau s plus 1, where tau is the time constant. So in that Maxon data sheet, it didn't give us the capacitance. It gave us the resistance and the time constant. So it's sort of setting you up to use this type of analysis. So 2.11 right there, that's the time constant from that data sheet. 1180 seconds, that's the other time constant. So as an example of the difference in the time constants, or the time it takes to heat these systems up, the winding time constant's around 2 seconds, so it heats up much faster. The housing time constant is over 1,000 seconds. What does that tell you about, like, if let's say you want to like judge your temperature by feeling the motor's housing? Is that going to work? Is that a good way to get an understanding of the system's temperature? No. It'll be 1,000 seconds for you to be able to feel the right temperature. I want to show you this. Okay, so this is this example. It actually is the example, this example comes from this robotic knee that I built when I was a postdoc. So this analysis uses the motor that's inside this knee, and then it uses a thermal input, which I want to describe, that's kind of geared to that situation. So this analysis came from the development of a robot, in this case a robotic knee prosthesis. So we have to go back to the question of what we wanted to do. So I created a thermal power input, this square wave pulse generator, but this is I squared R. I just happen to have it in this like pulse train format, which I would say I got this number, the I number. I got it from about how much current it uses each step. So the pulses are like step, swing phase, where it does very little. Step pulls the body up, that's a lot of torque. Then it goes to swing phase, it does very little. So I used a kind of a pulse train to represent when it's doing a lot of work and when it's not doing much. So that's just a kind of a way that I represented that to give you an idea. And if we look at the housing temp and the winding temp, it's going to show me the temperature increase from 0. So this is temperature rise, not, doesn't include ambient. So we have to add 25 degrees C to this to get the ambient temperature. And it shows how it heats up over time. If we look closely, we see it look like this. What's going on there? Yeah, anybody know?
Is it the stepping?
The stepping. So what we're seeing is the step, when the step, it rises really fast because that time constant is only 2 seconds. So as soon as there's a step, as soon as it's starting to apply power, its temperature is increasing. Then it went to the place where it was not doing anything, so then it starts to cool. Then the next step occurs, it rises, then it starts to cool. But if we look at it far enough zoomed out, it looks like it's just a regular response. We don't see the stepping at all. What would this be if we were just, let's say there's no stepping? How could I get this plot with no stepping, with no curves? what are we really looking at here? Yeah.
If you had your input was just flat, but like half the height of the amplitude.
Yeah, so looking at the step response to the mean of that stepping signal. So this is essentially like a step response. So if we just turned on the thermal power, how the system would heat up. Okay, so that's that. So you have access to this. You can use it by pattern matching. So you'd have to look at like the way the equations are laid out in the notes and then insert your values there. If you wanted to do this. This is like a little bit, I think this is something good for you to know, but I won't require you to actually do anything with the capacitances. Okay. Cool little MATLAB demo. Now I also want to show you, so like what happens if we don't, let's see. What is it doing? All right, there we go. Okay, so what happens if we don't know? So these properties, the thermal properties, are not commonly reported. So a lot of times we don't know these. Only that I've seen, like Maxon reports them, but most motor manufacturers don't. So if we want to understand these properties, we might have to determine these values ourselves. And I just want to show you like a quick video of how that might go. Okay, so what we did here was take a motor and just run 8 amps through it and film it with a thermal camera. When we filmed it with a thermal camera, we can measure its temperature rise. And you'll kind of like see this, it makes a really cool pattern. So we're measuring this particular motor. It's the first motor in that motor sheet that I gave you. It includes all of its thermal properties because we determined them. And we look at temperature as a function of time. We looked at fitting this model, the same model we just looked at, the thermal model, fitting this model based on the temperature data we collected. And that's how we obtained the values for the thermal resistance and capacitances. So it heats up pretty slowly. But this is kind of neat. So we did this, we published these values, and I think it was really helpful for a lot of people. But you might have, if you really care about designing this way, you might have to do that sometime. Also, a lot of these values are not provided. Okay. This is kind of like what you will have to know. This is taking this analysis and removing some of the parts that are more challenging, and you kind of will have to know this. So data sheets often provide the max, the max continuous torque or current. So a data sheet might provide this. This is remember when I said kind of at the beginning of the lecture, there's some shortcuts or rules of thumb that enable you to do this more quickly without that level of detailed analysis is this. So if you make sure that your current always stays under the max continuous current, or the torque stays under the max continuous torque, you're good from a thermal perspective. That's what they're trying to tell you by giving you those numbers, so you don't have to do an analysis like this. So if you do that, your design will work. Yeah.
If you like peak past the current, because I know it's saying continuous, like how long defines continuous? Like if you peak up above it for 2 seconds, then go back down for like 10 and then back up for 2.
Continuous is saying that if you look at the thermal response in those conditions, it will never cross the maximum winding temperature. So that the continuous current can run forever without ever overheating.
Okay.
It's usually the maximum value, and if you go higher than that, it will over time rise above their maximum permissible temperature. So if you look, this is from that Maxon data sheet. It's showing us nominal torque, max continuous torque, nominal current, max continuous current. It's just kind of giving us that information. So if you want to just design a robot that you know will work, you can use these max continuous values. If you want to make a system that's as light as possible, you can take advantage of the fact that the system has a delay or a set of dynamics. And that's what we do on the research end, we take advantage of the delay because a lot of times we know that the high torque required or high current only has to happen for a short time. And we can get a lot more performance if we allow the system to overheat. By this would mean we're operating way over the max continuous current or the max continuous torque. This analysis that I'm telling you, this framework allows you to do that, allows you to do those investigations to make the system not overheat given its thermal properties, even if you're trying to use it over the maximum continuous values. So this is sort of, you've learned the basis of this, and then I'm sort of not requiring you to know the thermal side of it. This is the thermal stuff we're gonna really focus on, but this is what a lot of people do this for a living. This is what we do in my research group, is to use that to our advantage. Okay. What we want to do now is think about, maybe let's not think about the dynamics, which is the transient response, how fast it rises. Let's just think about the final steady state value. Is that going to be above or below its maximum permissible value? So we're gonna ignore the dynamics, the capacitances for now, and say it's steady state. What's the current through a capacitor at steady state? 0. So at steady state, there is no current going through the capacitor, there's no flux going through that. It looks like this. So now we can do the same exact sort of set of equations. This is what you kind of will have to know. So R sigma total is going to be R sigma WH plus R sigma HA. Since they're in series, we just add them together, and now we have a total resistance. We know the delta sigma, so the temperature rise is going to equal Q of T times R sigma total. So now if I want to know what is the temperature change across the entire circuit, I can just use the current and the resistances to understand that. So there'll be a voltage drop or a temperature drop from here. There'll be a temperature drop from here. If I combine them, I can get the total temperature, or I can sort of look at the individual temperatures. Yeah.
What would be like the analogous state of a steady state, like thermal circuit? Like, what does that mean when the capacitor is full?
It means that the temperature of the metal has become the same temperature as its surroundings. It's no longer heating up anymore. It's gone through that entire process. So Q of T equals sigma W So between these sets of equations, you can determine the temperature rise. We have 10 minutes. I have a quiz for you. I think it's worth trying in 10 minutes because I don't know that next lecture. So I think we should do this. Read it, use these equations, try to solve it. I mean, it takes, if you know what you're looking